What specific problem does the dynamic cheat sheet (DC) framework aim to solve, and how does it improve the functionality of large language models (LLMs) during inference?
The dynamic cheat sheet (DC) framework addresses the critical limitation of large language models (LLMs) that lack persistent memory, causing them to approach each new problem without retaining insights from past interactions. By implementing a non-parametric memory that evolves during inference, DC allows LLMs to store and curate reusable strategies, solution sketches, and code snippets based on their successes and failures. This framework enhances the model's functionality by enabling it to retrieve relevant past insights before generating responses, thereby improving accuracy and reducing repetitive mistakes. For instance, DC significantly boosted the performance of models like Claude 3.5 Sonnet and GPT-4o on complex reasoning tasks, such as the Amy exams and the Game of 24, by allowing them to internalize effective problem-solving methods. Overall, DC transforms LLMs from static problem solvers into adaptive systems capable of iterative learning and refinement.
How does the proposed method DC work? Illustrate the methodology step by step, detailing how memory is utilized and updated during the inference process.
The proposed method, dynamic cheat sheet (DC), operates through a structured framework that includes two core modules, generation and curation. Initially, when a new query, x_i, is presented, the model accesses its current memory state, m_i, which contains previously stored insights and strategies. The model then generates a candidate solution, y_i, by combining the retrieved memory content with its internal reasoning capabilities. After generating the answer, the curation phase begins, where the model evaluates the effectiveness of its approach. If the solution is deemed correct or useful, it is codified into memory for future reference. If an error is identified, the model may revise or prune the faulty strategies. This iterative process allows the model to learn from successes and failures without requiring gradient-based updates, thus maintaining compatibility with black box APIs.
Can you provide a simple example that demonstrates the inner workings of the dynamic cheat sheet algorithm? Walk through the main algorithm steps using this example to showcase how insights are stored and retrieved.
A simple example to illustrate the dynamic cheat sheet (DC) algorithm involves solving the Game of 24, where the goal is to combine 4 digits into an arithmetic expression equaling 24. Initially, the model receives a query with 4 numbers, say 7, 7, 8, and 11. The first step is the solution generation, where the model uses its internal reasoning to propose a solution, such as 8 * 7 plus 7 to 11. After generating this answer, the model enters the curation phase, where it evaluates the correctness of the solution. If deemed correct, this approach is stored in the external memory for future reference. In subsequent queries, when presented with similar sets of numbers, the model retrieves the stored solution, allowing it to bypass manual calculations and directly apply the previously successful strategy, thus demonstrating the iterative learning and memory curation capabilities of the DC framework.
What theoretical and practical benefits does the DC framework offer compared to existing methods like dynamic evaluation or retrieval augmented generation systems?
The dynamic cheat sheet (DC) framework offers several theoretical and practical benefits over existing methods like dynamic evaluation and retrieval augmented generation systems. Theoretically, DC provides a persistent, evolving memory that allows black box LLMs to learn from past successes and failures without requiring gradient-based updates, thus preserving the model's core parameters and ensuring compatibility with commercial APIs. Practically, DC curates a compact library of reusable strategies and insights, enabling the model to selectively store and refine knowledge, which enhances its problem-solving capabilities and reduces repetitive errors. For instance, in benchmarks like Amy and Game of 24, DC significantly improved accuracy by allowing models to retrieve and apply previously successful strategies, whereas traditional methods often lack this iterative learning capability. Additionally, DC's structured memory curation prevents the inefficiencies associated with appending entire conversation histories, ensuring that only valuable insights are retained for future queries. Overall, DC's approach fosters a more efficient and effective learning process, particularly in complex reasoning tasks.
How is the effectiveness of the dynamic cheat sheet method validated? Describe the experimental design, datasets used, and the specific metrics applied to assess its performance.
The effectiveness of the dynamic cheat sheet (DC) method is validated through rigorous testing across multiple challenging benchmarks, specifically focusing on tasks that require complex reasoning and iterative learning. The experimental design includes evaluating state-of-the-art language models like GPT-4o and Claude 3.5 on datasets such as the AMY exams, GPQA Diamond, Game of 24, Math Equation Balancer, and MMLU Pro, which are selected for their demand for multi-step reasoning and strategic adaptation. Performance is assessed using tailored accuracy metrics, soft match (SM) for GPQA Diamond and MMLU Pro, and functionally correct (FC) for Game of 24 and Math Equation Balancer, ensuring that the evaluation aligns with the specific requirements of each task. The results demonstrate significant improvements, such as Claude 3.5 Sonnet's accuracy on AMY 2024, increasing from 23.3% to 50.0% under DCRS, highlighting the method's impact on reducing repetitive errors and enhancing test time learning. Overall, the combination of diverse datasets and specific metrics provides a comprehensive assessment of DC's capabilities in fostering effective memory curation and retrieval.
What were the key results achieved with the new method, particularly in terms of accuracy improvements on benchmark tasks? Can you point out any notable differences in performance across different models or tasks?
The dynamic cheat sheet (DC) method significantly improved accuracy across various benchmark tasks. For instance, Claude 3.5 Sonnet's performance on the AMY 2024 exam surged from 23.3% to 50.0% under DCRS, while GPT-4o improved from 20.0% to 40.0%. In the Game of 24, GPT-4o's accuracy skyrocketed from 10% to 99% after implementing DC, showcasing its ability to learn and refine solutions effectively. However, smaller models like GPT-4o Mini exhibited limited gains, with performance stagnating or declining, indicating that the effectiveness of DC is closely tied to the model's generative capacity and ability to produce high-quality solutions. Notably, while Claude 3.5 Sonnet showed substantial improvements across tasks, GPT-4o's performance varied, with slight decreases in more complex domains like MMLU Pro, highlighting the impact of model scale and task complexity on DC's effectiveness.